Welcome back to Perry University. We're going to continue the discussion on logics. Today we're going to do logic gates and truth tables. And at the end, we're going to go through 3 practice problems just to kind of get used to them. Feel free to like, subscribe, comment what you don't like, what you do like. Only if you feel like I deserve it though. All right, let's get into it. All right, let's talk about the basics of logic gates. So first, these are digital and they're combinational asynchronous circuits. Some pretty important terms right there. So digital, there's going to be up, down, that's 0 or 1. It's not going to be all over the place like analog. Combinational, so that means it depends only on the inputs. It doesn't hold any memory. To kind of go ahead and give you the definition of sequential, which is the opposite of combinational, that's when the inputs and the past states affect what's going to happen, and that is a memory. That is not what we're doing here. For now, we're just going to focus on combinational logic. Also, they're asynchronous, which means no clock. That means it only depends on when the human inputs something. Their name is going to imply their function. An AND gate is going to be just that. It's an AND gate, an OR gate is an OR gate, NOT gates are NOT gates. Pretty straightforward stuff. All right, so for these, something that's really important is you can have as many inputs as you want, but you can only have a single output. For instance, let's take this poorly drawn OR gate as an example. You can only have one output. That's going to be your function. But you can have 2 inputs, 3 inputs, 4 inputs, 5 inputs. It doesn't matter. You can have as many inputs as you want, but only one output. Another crucial component, no loops. So this can't branch off of here. This wire can't come back around and then feed back into it. That, not allowed. First, let's talk about buffers. Buffer basically doesn't do anything. It can be used as an amplifier, but for the sake of this level, it doesn't really do much. So for here, you're going to have one input, A, and the output is going to be F for function. Bear in mind, you can use whatever letters you want. I just like using A, B, C, D for inputs, and I like F for output as a function. And whatever the value of A is, that's going to be the value of F. So if A coming in is 0, it's going to go through here and come out as 0. If A comes in as 1, it's going to come out as 1. So now let's look at this thing on our left. Let's talk about this. This is a truth table. So all this is showing is for every input of A, what is your function F going to be? If A is 0, F is 0. If A is 1, F is 1. Now let's take that buffer and turn it into a NOT gate. We're going to have our triangle again with A coming in as an input, but this time we're going to add a little circle that indicates that it's a NOT gate. This little bubble means whatever gate you have, it's not whatever it would normally represent. So this triangle is normally the buffer. If A is 1, F is 1. If A is 0, F is 0. It flips it. So now we have A coming in. If A is 0, then F, let's draw F over here, then F is going to be 1. If we have a 1 coming in, F will be 0. That's a NOT gate. All right, now to get a little bit more complicated. And let's start drawing out our truth tables. So next is an AND gate. To draw an AND gate, kind of draw 3/4 of a square, then you put a round edge on your function output side. And let's just use 2 inputs, A and B. Let's take this and draw a truth table. So we have A as an input, B as an input, F as a function. Draw our lines. Okay. So we're going to start out with 0, 0, 0, then 1, 0, 1, 1, 0 for 2, 1, 1 for 3. And remember, that's 4 possibilities. So we have A and B are both 0, A is 0, B is 1, A is 1, 1, B is 0, or they're both 1. Now, like the name implies, AND gate, for F to be true, A and B need to be true. So A and B have to be 1. Let's go back to the truth table. We have 0 and 0, so F is going to be 0. 0 for A, 1 for B. Is A and B 0? Nope, just B. So F is still 0. Now we have 1 and 0. A is 1, B is 0. So we don't have A and B as 1, so again, F 0. Now A is 1 and B is 1. F is on. So that's going to be your AND gate. OR gate, as the name implies, it can be A or B. Let's go ahead and draw it. So now we kind of have this curve, and then this kind of spaceship looking thing. Here comes function f. Again, let's just do two inputs, A and B. There we go. Draw a truth table, A, B, F, and you're going to need to get really used to drawing these really fast. 0, 0, 0, 1, 1, 0, 1, 1, which don't worry, I promise you will. All right, so now we have A or B has to be on for F to be on. Let's go ahead and number our rows as well. We have rows 0, 1, 2, 3. We have two variables, A and B. And if you're wondering how many rows a truth table is going to have, it's 2 to the power of however many variables you have. So it's 2 to the power of, we have A and B, which is 2, so 2 to the 2 is 4, 0, 1, 2, 3, that's 4 rows, there you go. All right, is A or B on? Nope. Is A or B on in row number 1? Yes, B is on. Same thing for row 2, we have A on, so automatically we know F is on. And now we have both A and B on, which means F is on again. Real quick, let's do an OR gate that has A, B, and C. Let me sneak C in there. There we go. So now we're going to have how many rows? 2 to ABC, that's 3. 8 rows. So we have A, B, C, function F. All right, we're going to just count in binary up to 7. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And let's just double check how many rows we have. 1, 2, 3, 4, 5, 6, 7, 8. Yep, that's it. And because this is an OR gate, only one of these inputs needs to be on. A, B, C in row 0 are all off, so F is off. And then from there on, there's a 1 in every single row. So we'll just draw a 1 all the way down. So those are the states where F is going to be active. If only C is active, F is a 1 as well. If only B is a 1, but A and C are both zeros, F is still a 1. If all A, B, and C are 1, again, F is going to be a 1. So now let's talk about NOT gates, but with the AND or OR gates. So let's start with a NAND. So this N just means not. So to make a not AND gate, all you do is draw your AND, make a curve there, and put a little circle on it. Now you know it's going to be not AND. There's your function. And we'll use inputs A, B. Let's draw a truth table. So we have A, B, F, 0, 0, 0, 1, 1, 0, 1, 1. So if it's not and we have an and down here at the bottom, because we have A and B are both on, and it's not that. So if A and B both come in as a 1, so we have 1 and 1 coming in, and F is going to be true, not when that's happening. F will be 0. So let's go down here, make this a 0. In all other cases, F is going to be true. So 1 and 0, 0 and 1, 0 and 0. And if you notice, anytime you have a NOT gate, it's just the opposite for whatever the normal gate is. So let's do NOT OR. So to draw a NOT OR, draw your OR gate. There we go. Let's put a bubble on it. Function A and B. Let's go ahead and put in a truth table. All right, and we know it has to be NOT OR. So normally an OR gate would be anytime one of A or B is true, then F will be true. So it would be 0, 1, 1, 1. But now we're going to do the opposite. Let's look at the first row. Do we have A or B? We don't. That would make F true because it's not OR. But now the other 3 rows are true for an OR. But we want not OR, so we do 0, 0, 0. Now a trickier one, exclusive OR. Exclusive OR is just like OR, except it's only one of them. So here's our OR gate, and to make it exclusive, we put that curve in front of it. All right, make a truth table. All right, so with exclusive OR, this is like a restaurant where they ask super salad. They're asking if you want the soup or the salad exclusively, not both. But they're asking if you want one or the other. So neither would be off. And now we go to the next row. We have B is on exclusively, so that's true. For the next row, we have A on exclusively, so it'll be true. And then finally, we have A and B, but they're not exclusive, so it's off. Now we get to the exclusive not OR gate. At this point, I feel like you should be pretty competent in drawing these because you know we're going to have an OR gate. Let's make it exclusive, and let's make it a NOT. And we'll have two inputs, A, B, for output function. So now, if our last one was an exclusive OR gate, this one's going to be the opposite. It's not exclusive OR. So we know in the last one, exclusive OR was when A or B exclusively were true, but no other cases, which led to 0, 1, 1, 0. So now let's think about just doing the absolute opposite of this, which would be 1, 0, 0, 1. And that's what the truth table is going to be for an XNOR gate. Let me get rid of these and fill it in properly so you have the actual answer. 1, 0, 0, 1. And that's it. Let's work on some practice problems. Number 1, a security system receives signals from a key and a pin. All right, so there's a pretty good giveaway right there. And we have two inputs right now, a key and a pin. The doors controlled by the system will unlock if the key is present and the correct pin is entered. Draw the truth table for the system and determine the logic gate. So first, let's determine our inputs. We have an input key, which I'm going to call K. We have input pin, I'm going to call that P. And the door unlocks, just call it door for the output. Okay. So when the key and pin are present, we're going to have an AND gate to unlock the door. So let's draw that truth table. So the first row, or row number 0, neither key or pin are there, so 0. And then rows 1 and 2, we only have key or pin, not both. So the door still won't unlock. But then in row number 3, we have key and pin, which means the door is going to unlock because both are present. And it asked, or well, it stated, the door is controlled by the system will unlock if the key is present and the correct pin is entered. And there we go. So we know it's going to be an AND. So it would look like this. That's what it would look like as a circuit. All right, problem number 2. A sprinkler system in a garden provides water for the plants. There are 3 rain sensors in the garden. If a signal sensor detects rain, the sprinkler system will not turn on. So let's be careful with the wording here. So we have 3 rain sensors in the garden. If a single sensor detects rain, the sprinkler system will not turn on. So if only one sensor detects rain, then the sprinkler system remains off. So first, let's think about our variables. We have 3 sensors. Let's just call them S1 through 3. So S1, S2, S3. So we know what the truth table is going to look like. It's going to be 8 rows because we have 3 variables. So we have 0, 0, 0, 0, 0, 1, and I'll just skip ahead. So that's going to be the truth table for the sensors. And let's just call our output, we're just going to call it function. It'll represent the sprinklers. So we'll draw our lines. Okay, so if any one of them detects rain, then the system will not turn on. All right, so it turns on only when all 3 are not detecting rain. So in the first row, or row number 0, if you will, sensor 1 does not detect rain, sensor 2 does not detect rain, and sensor 3 does not detect rain, which means the system will water the garden, so it will be on. And from there on, if any one of them detects rain, then our sprinkler system is off. And you can see, just looking down this, at least one of them is on for every other row. So that's what we end up with. Now, what gate is that? This to me looks pretty suspiciously like the opposite of an OR gate, which would be a not OR or a NOR gate. So let's draw that. I'll have 3 inputs, S1, S2, S3. All right, problem 3. Hallway light is controlled by 2 switches, one at each end of the hallway. The light is on only when exactly one of the switches is on. Okay, so we have two switches, switch 1, switch 2. Let's call those S1, S2, and let's have our variable be light, we'll just call it L. The light is on only when one switch is on, and only exactly one switch is on. So first, let's finish this truth table. All right, now let's determine when L is going to be turned on. One switch is on, L is on, but only one. So here we have switch 1 is off, switch 2 is off, so we know our light is going to be turned off. Now we come to switch 1 is off, but switch 2 is on, so one light is on, and only one light, which means our light is on. Next we have switch 1 is on, switch 2 is off, again only one is on, which means our light is on. Then finally, rows 0, 1, 2, 3, we have switch 1 on and switch 2 on, but that means our light is going to be turned off because only one switch can be on. So what gate is this? This is going to be exclusive to one at a time, which is exclusive OR. So to draw exclusive OR, we draw an OR gate, and we put that line or that curve in front of it. Inputs S1 and S2, output L. And that's what it's going to look like in a circuit diagram. Thanks for sticking with me. I hope you got something out of this. I hope you learned something today.